Hello, I'm here today to talk about timing and sync. I apologize about my room. I'm in a little bit of a weird living situation presently. But I thought today I would talk to you guys about timing and sync. We're going to talk about those terms real quick right here, which is basically that timing is the process of creating a signal that denotes time, whereas synchronization is when we apply that to multiple devices to kind of get the whole system operating at one level. In our industry, the word reference has kind of been thrown around to mean both of these things, but I do want to have a slight distinction between the two, whether I'm referring to timing signals or devices being in sync. Really, we care about this because of latency, and we see latency and hear latency in live applications as lip sync errors. Our ears are really good at finding lip sync errors. We can figure it out within about 66 milliseconds, or about 2 frames, in most video applications. So we can really just it's not acceptable. It's not really what we kind of think of as a broadcast standard. So we can solve this. The simple answer is to use a clock, or a master clock, to be more specific. Every digital device has a clock. Even your computer has a clock running in it. That kind of determines when each process happens and how often things can be changed or monitored. But we can use a master clock to create to create multiple timing signals that happen at the exact same time, which can be really useful for actually syncing our devices together and providing a real reference point for all of our devices to talk on. Sync generators usually make a bunch of different actual signal types, which can be used to sync different kinds of devices. This process is called gen locking. No, there is not a key. So most modern sync devices, or sync generators, can create bi-level, tri-level, which are both video reference signals that contain black burst, and also word clock and time code, which is really what we're going to be talking about. I did prepare a small slide here about the back of a sync generator. You'll see on the right side you have those XLR inputs, which give us our actual linear time code, which we'll get into in a minute, as well as a bunch of other video signals, including word clock, which is most important for audio application. And the reason it's important is because of digital sampling. We have to have some form of digital sampling because analog signals are not compatible with digital devices. Analog audio is a little bit easier to work with in the sense that it does not require a timing signal because it is just a wave. It works intrinsically in real time. But as soon as we start trying to turn those waves into bits and to make them digital signals, we have to make sure that all of our devices are kind of making sure that the beginning of our refresh rate or our sample rate are happening at the same time, which can be done generally through word clock, which we'll get into in just a second. But I just want to remind everybody that we're looking at 48K and 96K for most of our live applications. So that's just something important to remember for when we get into our actual time code stuff. So here's an example of a word clock signal, as well as some basic information on it. A word clock signal is just a square wave. It's a relatively simple signal, but it's really important because of its kind of lack of ambiguity. It's a very clear signal. It's either kind of a 1 or a 0 as far as a digital system is concerned. And it can be moved over 75 ohm coax cable or 110 ohm AES cable, where it is known as DARs, or digital audio reference signals. It can also be embedded directly into your digital audio stream, which can be very valuable in applications that you might not want to run additional cabling for each and every device. But we can look at what happens if we don't do that, which is we'll have a desync, very simply said, where our devices might not necessarily be kind of on the same page about when timing begins. And when we start sampling and having two samples that are not exactly right, not exactly on the same timing, we start to hear those as pops and clicks as those kind of signals interact with each other. Those pops and clicks can be very distracting, so we try to avoid that as much as possible. And we can start talking about jitter. Jitter is basically just a function of poor clocking, as well as it can be affected by electromagnetic radiation or temperature fluctuations in extreme cases. But we can hear jitter as kind of a high frequency distortion. It basically happens when our audio doesn't necessarily reference to the exact same point and is offset by a small margin. So we can fix this by using more resilient clocks that can handle the environments we're in, or just by replacing our gear that cannot clock or cannot get into the master clock signal or the gen lock effectively. There's deterministic and random jitter. Deterministic jitter usually has an identifiable source and can kind of be tracked down, whereas random jitter is kind of beyond the system that you're actually working in. But expanding slightly from just talking about strictly audio, we can start talking about timecode. Timecode can be really, really useful, especially in post-production editing, because we can actually kind of stamp that onto other signals. The current standard is SMPTE 12M, which is about an 80-bit per frame system. It was established in the 1970s by SMPTE. No surprises there. But it's been modified a few times, or updated rather, to account for digital applications as well as differing frame rates. Outside of video, it's usually just called SMPTE, but we have to be a little bit more clear because we have lots of SMPTE standards that we use. Generally, this will also be output by your master sync generator. You can also have a separate tricode generator, which is really common in like audio studio applications. But in our live world, we kind of assume that it's going to be on our master clock. A couple versions to think about are your drop frame and non-drop frame, which are basically just our ways of dealing with 2997 versus 30 frames per second. Just check with your engineer to make sure you know which side you're kind of on. Looking at the graph here, we can kind of see what this actually looks like, where we can see, kind of how big the frame is. And then there's a bunch of user bytes as well as some other information that gives us kind of an exact idea of when things are happening. These 80 bits can give us lots of information about camera numbers or real numbers or take numbers, which, again, very useful in the post-production edit. Realistically, we also need to differentiate between linear timecode and vertical interval timecode, or LTC or VITC. LTC in particular is really nice because it has a bandwidth of about 2400 hertz, which means that it is below our 48K that we mentioned earlier, which means that it's actually compatible with a lot of our standard audio equipment, especially our analog audio equipment. You can send it over XLR cabling and also over analog video equipment using 75 ohm coax cabling. This can be really useful because we can actually just throw it on a track in an ISO deck or on a Pro Tools session while we're doing our ISO records or our stem recordings, so that we can have, again, a synced idea of when different signals are happening within that deck or within the Pro Tools session. Vertical interval timecode, or VITC, is a little bit beyond the scope of our discussion because it's primarily used for analog video signals, but it basically just also has the an ancillary vertical blanking period, which gives us better ideas of what's happening on each interlaced field of video, which is not a super important standard anymore, but it's important to know that this exists so that you know whether you're on VITC or LTC. Other cool things about timecode, it can actually be put directly onto an AES-3 digital audio stream, and it can be embedded into that, which is really nice, again, for making sure that we can see when things are happening in our post-edit. But it can also be moved over MIDI It's a slight variation on the original 12M timecode that we're used to, but we can actually send it directly over MIDI to instruments and music and also other MIDI devices, so that those devices can be synced relative to each other. Again, multiple versions of this exist. We can see anything from like 24 to 30 frames in drop and non-drop versions. A really good master sync generator is really going to give us everything we need: bi-level, tri-level, which are for video, as well as word clock and timecode. And that's kind of what we're looking at in our live production environments. In our studio environments or in more controlled environments, this becomes less of a concern. But it's always important to remember whether or not we are clocked and kind of where we're actually kind of trying to move as far as getting our signals perfectly aligned so that we don't have any lip sync or jitter issues like we talked about earlier, as well as just kind of making our post-production editor like us with our application of timecode. So thank you for listening to me yap for a little bit about clocking and sync. But I think it's important that we all kind of have a basic understanding and idea of where these signals come from, so that we know how we can apply these and how we can make some creative solutions to strange problems that we might not be used to. Thank you.